Hello guys, welcome back to my YT channel. This is again I'm a singer Eternal Voice. So at this point in time, we're gonna vlog or live stream pertaining to the relationship and correlation of fluid mechanics and also the thermodynamics. So we need to point out or find out what's their similarities and what's their differences, something like that. Okay, so before anything else, I would like to illustrate so that we can have a little bit of idea regarding their relationship. Okay, so there's three topics or subject matters or coverage subject matter. Okay, it's gonna be like this. Oh my god, wait for a while guys. Aren't ko masango sa pag kasi what? So because what na important is I don't have and okay, fluid mechanics, heat transfer, and thermodynamics. It's gonna be like this. Ting, 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 ting. Okay, like this. Okay, the relation between these three topics or subjects, fluid mechanics and the momentum transfer. Okay, basically fluid flow and then you have thermodynamics and then the heat transfer. Heat transfer are very closely related to each other because their driving force are temperature gradients or temperature differences. Okay, so there's no question about this. So we need to focus first for the fluid mechanics. So the parent subject, or shall we say, a scientific principle for this fluid mechanics is under momentum transfer. Okay, then momentum transfer. Then after that, you have the fluid flow. The fluid flow consists of fluid mechanics, fluid dynamics, and fluid statics. Okay, so in that, we need to understand the law of continuity, the law of steady state. Okay, and then you have the continuity equation. Okay, the relationship between mass flow rate and volumetric flow rate. Okay, of different substances, particularly fluid, liquid, and gases that will flow in a streamlined condition. Okay, in this fluid mechanics. Okay, so we need to account the fluid mechanics under fluid flow, right? Using, oh my gosh, grabe, grabe ka ano. Teka sa guys, this one. Using Bernoulli equation. Okay. And then in this fluid mechanics or fluid flow, okay, this is related to momentum transfer, which is our driving force is the velocity grade, the velocity changes. Okay. Okay. So the equation will be, this is the parent equation. We have the pressure, that's 1/2 density v squared plus density gh is equals to constant. Equation number 1 is 1. Pressure, the fluid static pressure plus 1/2 density v squared is dynamic pressure plus density gh is the potential pressure, or what we call as the hydrostatic pressure. It's equal to the constant. Okay. So we will just memorize this general formula and everything will follow. Okay, for energy. Okay, and this is dynamic pressure related to energy, and it's potential energy. Okay, and in relation to the hydrostatic pressure also. Okay, now if we obtain an equation that deals primarily with the height or the head form, because this is the general form, right? So head form, we're gonna multiply this by 1 over density gravity, that's the gravity. So 1 over density gravity. So it will become now pressure over density gravity. Okay. Pressure, density, gravity, plus, so okay, density will cancel, right? Here, it's gonna be, okay, V squared 2G plus H constant. This is equation number 2. This is the head form or the elevation form, this one. Okay. Okay. This one. Head form is the general form in terms of pressure form, right? And then we go to the energy form. Okay. In going to the energy form, we take into account the constant mass of the fluid that will go inside your medium. Okay, so if the pipeline, nozzle, let's say ventilator or distributor or diffuser or whatever, cells that have several connections of pipelines, physical connections of pipelines, right? Okay. So we need to consider that the mass will be constant in the entire flow. So we need to have to say you have the idea already, the kinetic energy, potential energy, like that. Okay. And also static energy, right? Even though is at rest, that's also static energy have also, right? Okay. So we need to multiply this parent equation by, take note, by 1 over density, right? So it's gonna be like, so 1 over density na siya. So, okay. Density, gravity, H is 1 of multiplied by 1 over density, it will become GH, right? And then 1/2 density V squared times 1 over density is equal to 1/2 V squared. And P times 1 over density is equal to P over density. So it's gonna be like this energy form. Okay. Nakakaloka. Our energy form class will be, oh, like this. So pressure over density plus 1/2 K squared plus GH. And this is our equation number 3. And this is our energy equation. Energy form from the Bernoulli theorem, Bernoulli equation. So only the mass and the kinetic energy has been eliminated, and only the mass in the GH. G is the acceleration due to the gravity. Supposedly there's a mass here also because we treat mass as constant, okay, something like that, or doesn't have contributing factor in the change of your equation, something like that, or should we say not really have a great factor, something like that. Okay, to have a very irrelevant factor throughout the process, something like that. Okay, and this is one. Okay, now in order we can determine if it's laminar or turbulent flow, we need to use the Bernoulli number, Reynolds number, sorry, not Bernoulli, Reynolds number. Okay, Reynolds number is equals to the inertial, okay, inertial force over the viscous force. Okay. Reynolds number, inertial force to viscous force in directly is equal to the density, that's velocity, that's the length over the mu, like this. Viscosity, this is dynamic viscosity. And your dynamic viscosity will be equal to the length squared over the time. Okay, like this. Dynamic viscosity length squared over the time, or it should always equal to um, another is the kinematic viscosity times the density, this one. You also equals to kinematic viscosity times the okay, density. Okay, so it's either you will use this one, the Reynolds number equation here, or either this one. Okay, so it's gonna be like that. So Reynolds number less than 2100 laminar flow, above 2100 is turbulent flow. It's very important in fluid mechanics and fluid flow. Okay, and, and then we need also to relate this to the momentum flux or shear stress, like that. So shear stress is equals to like this. Okay, pressure times area. Okay, shear stress, pressure times area. So the unit of shear stress is really Newton. Okay, like this. Pressure times area. So try to see, this is shear stress, this is shear inertial force. Shear stress equals to pressure times area. Try to equate that here in your inertial force if it is equal. Let's investigate in your numerator. Okay, this is density, kilogram, cubic meter, volume, cubic meter, and length, meter. Like that. Density, this velocity, sorry, this is velocity, the small v. If I told you, okay, small v is velocity, right? It will confuse us the letter small v and letter capital V, but I automatically corrected that now to velocity. So it's a meter per second. Okay, cancel, cancel like this. It's gonna be cancel, cancel. This is kilogram meter per second. Okay, over your viscous force with S. It's also the dynamic viscosity, kilogram meter per second. So kilogram meter per second divided by kilogram meter per second. Okay, so cancels out, cancels out. So this is unitless. Okay, it cancels out. Okay, this is dynamic viscosity, unit kilogram meter second, and kilogram meter second for your initial force, which is also equal to your stress. Okay, and shear stress is gonna be this one, density, that's velocity, that's the length, and substitute and plug in the units of each density, velocity, and length. Then you can obtain this kilogram over meter second over the dynamic viscosity, which is kilogram meter second. Okay, unit man is siya, ang dynamic viscosity kilogram meter second, or it could be Pascal second, or it could be a poise, 1 Pa, something like that. Okay, but the kinematic viscosity here, this one, with wings, small letter V with wings, is centimeters squared per second, something like that, and something point, something like that. Okay, you can rearrange your formula and determine the exact cancellation of similar units, and then you can obtain your proper formulas and equations, something like that. Okay, it's very important in the fluid mechanics. Okay. Now, if you relate this to transport phenomena or the momentum transfer, it's gonna be like this: mu dv dz. Okay, like this. It's gonna be your shear stress or momentum flux. Okay, then momentum flux is equals to kinematic viscosity times density, dV one. Momentum flux is equals to the kinematic viscosity times density, dV dt. And dV here is the change in velocity gradient from higher velocity to lower velocity of your fluid molecules moving in a streamline, something like that. And then dz is gonna be the horizontal axis that this you can have the velocity profile. Okay, and you have your z here. Okay, vertical y and you have the z here. For example, only these are you can say also that it's x. It depends on you, but in the book it represented as z matchup. So z, so it could be this velocity profile here, huh? Velocity profile going here, going here, going here, going here. Okay, Ganon. So that is your fluid mechanics. And we'll be able to continue this tomorrow. Let's talk about thermodynamics and heat transfer, but let's gonna consider first thermodynamics, right? Because it's a little bit, should we say, not really that complicated enough compared to the heat transfer. Thank you so much, guys, for watching this live stream for a matter of 16 minutes. If you want to comment this live, then you can comment below in the comment section. And you can subscribe my YT channel if you're not subscribed yet. And you can click the notification bell for some news updates of everything I mentioned. Bye bye, everybody.